In this video, we'll be looking at wave properties and equations, getting some of the basic principles of waves and some of the basic equations that go with waves with some example problems. There are two major types of waves that we're going to look at. There are transverse waves and longitudinal waves. A transverse wave is a wave in which the particles are vibrating perpendicular to the direction that the wave is traveling. This is what you most commonly think of with an ocean wave. An ocean wave is a transverse wave. The peaks, the crest and trough, what we refer to as the peak of the wave and the bottom of the wave, the trough, are traveling in a direction perpendicular up and down to the way the wave is traveling, say, for example, in this picture, left to right. Another example of this type of wave is light. Light travels as a transverse wave. So light travels in one direction, the peaks and troughs go in a perpendicular direction. The second type of wave is a longitudinal wave. A longitudinal wave is a case where the particles are vibrating parallel to the direction that the wave is traveling. So here, for example, you see the peaks of the wave on this drawing down here below. The peaks, this thick area here, and then it gets really spread out, the troughs, and it's traveling in the same direction that the wave is traveling. So you actually see the wave compressed together and spread apart. If you were to take a slinky, stretch it out and pull one in and let go, that would be a longitudinal wave. A sound wave is also a longitudinal wave. So sound will be a longitudinal wave, light will be a transverse wave. Now, there are two major types of waves that we look at. There are individual wave pulses, or for example, you have a single pulse traveling down a wave. Here you see in the picture on the top, a person shaking a rope or a spring and sending an individual wave pulse down the wave. The wave is traveling to the right, the pulse is up. This is a transverse wave. Here's another transverse wave, but this is a periodic wave where it's a constant wave like this. That, like you would see a light wave traveling by, you see these constant peaks and troughs, and you see the various parts of the wave continually. Now, there are a number of different properties of waves that we want to understand. The first one is amplitude. Amplitude, by definition, is the maximum displacement from its equilibrium position. So if the wave starts at the zero position here, how high it goes or how low it goes is the amplitude. The symbol we use is capital A, and the units are meters. So the blue wave would have a really large amplitude, an amplitude of 100. The green wave would have an amplitude of 60, whereas the red wave would only have an amplitude of 20. So it goes 20 up and 20 down. That would be a low amplitude. The second principle is wavelength. Wavelength is the distance between two adjacent points on a wave. Wavelength is given the symbol lambda, Greek letter lambda, and it's the distance between two of the same points on the wave. You see it drawn here from the 2 points, the top of the two waves. You can also have wavelength from this to this, the crest of the troughs of the wave, not the crest. You can also have it from where the wave starts to where the wave starts going up again. That would be the wavelength. So there are many different points where you can identify the wavelength. Two of the identical points on the wave gives us the wavelength. This is also in meters. Third is frequency. Frequency and period are indirectly related ideas. Frequency is the number of wave cycles per second, given in the units of hertz, whereas period is the amount of time it takes for a particle on a wave to complete one cycle. So we'd already looked in circular motion at period and frequency, but period and frequency, remember, are inversely related to each other. They're the opposites. So period is 1 over frequency, or frequency is 1 over period. A couple of key relationships with waves. First, energy is directly related to frequency. So the more energy a wave has, the higher the frequency is going to be. And wavelength is inversely related to frequency. So the longer the wave is, the less frequent it's going to pass the same wave traveling at the same speed. If you make the waves closer together, they pass more often. The main equations that come out of waves. velocity equals frequency times wavelength, and the frequency equals 1 over period, or period equals 1 over frequency. We'll use these two equations when solving problems for waves. The main one here is going to be this top one, but we also will use the bottom one for switching between period and frequency. Now, light. Light is a transverse electromagnetic wave, so it's a pulse of electromagnetic energy traveling through space as a transverse wave. It travels at an incredibly high rate of speed, 3.00 times 10 to the 8th meters per second, and that is a constant speed for light at any point in the universe. Sound is a little bit different. Sound is a longitudinal pressure wave, so it's the pressure of whatever medium, air usually, that it's traveling through that causes it to have its peaks and troughs. When the air molecules are pressed together, those are the peaks. When it's pulled apart, rarefied, that's the troughs. Light travels at a significantly slower speed of about 343 to 360 meters per second at room temperature through air. It depends on the temperature of the air, it depends on the density of the air. Sound travels at much higher rates of speed through more dense mediums, so through water, through metal, it travels significantly faster. Through less dense things like air, it travels slower. So speed of sound, significantly slower, 360 meters per second versus 3 times 10 to the 8th meters per second. Humans can hear sound waves generally in the range of 20 to 20,000 hertz of frequency. The older you get, the less you are able to hear at a higher frequency range. And that your ability to hear higher frequency sounds decreases as you get older. Hence that ringtone that some people try to sell as the ringtone that adults can't hear, being a really high frequency ringtone. Different frequencies give us different musical notes, and the level of sound is measured in decibels, how loud sound is. And the interesting thing is sound level is on a logarithmic scale. So if you go from 10 to 20 decibels, that's not twice as loud, that's 10 times as loud, because it's on a logarithmic scale. So every step larger, 10 to 20, is actually power of 10 larger. Let's look at 2 example problems to finish this up. Suppose you're standing on a boat in an ocean looking out at a person swimming in the water. The waves swell under your boat with a frequency of 1 hertz, while traveling with a speed of 2 meters per second. At any given moment, you can count there are exactly 10 waves between you and the swimmer. How far away is the swimmer? Well, we know velocity equals frequency times wavelength. The velocity here is 2 meters per second. The frequency is 1 hertz. So we can solve for the wavelength. The wavelength of this wave is 2 meters. There are 10 waves between you and the swimmer, so 2 times 10 means the swimmer will be 20 meters away. Second, the sound wave bounces off a cliff and is heard 2.5 seconds after the person speaks. How far away is the cliff that caused the echo? So, we're taking our sound wave, and we're going to look at our sound wave and use our distance. Velocity equals frequency times wavelength, but we also remember velocity equals displacement over time. In this case, the original equation will be a lot more useful to us. We use the 360 meters per second value that I gave in this slide. We'll see different values depending on different temperatures of the air. We want the distance and the time, 2.75 seconds. Now this is what I expect us to do in this case. We multiply 360 times 2.75. To give you a distance, 990 meters. Now, this is a very common mistake because people come back to them. So it's really, what we just solved for is the distance from the person to the cliff and back. What we really need is it only takes half of that distance to reach the cliff. The cliff is only 495 meters away. So that gives us some basic principles of waves and some basic examples of the types of problems we can see with waves. We'll look at more examples of problems in class.